Hello everyone, I am Vignesh Ramasubramanian and I am here to present my course project for wireless communication. My project title is Performance Analysis of Training Based Channel Estimation in Rician Multiple Input Multiple Output Channels with Kronecker Structured Rician Fading at the University of Florida for the course EEL 6509 Wireless Communication under my professor Dr. Dapang Oliver Pugh. Uh, First of all, let us take an introduction into fading. Fading is a phenomenon that is predominantly existing in cellular communication channels. Interference in channels connecting the transmitter and receiver causes the signal traveling from the transmitter to receiver arrive at the different times at the receiver. This deviation causes attenuation of the signal during propagation. This attributes to fading. The categories of fading are large scale fading, small scale fading. Large scale fading is further divided into path loss and shadowing effect. Small scale fading is further divided into multipath delay spread and Doppler spin. The multipath delay spread is further subdivided into flat fading and frequency selective fading. This flat fading and frequency selective fading are the main criteria that will be considered in my project. First of all, let us take a look at what is multipath propagation. Signal traveling from the transmitter to the receiver takes multiple reflective paths. This results in interference and phase shifting of the signal. Uh, inter- Interference can either be constructive interference or destructive interference. Fading usually occurs due to destructive interference, and when one component dominates, Rician fading is suitable, and when the magnitude of the signal resembles the probability density function of Rayleigh distribution, then we call it as Rayleigh fading. There are different techniques to reduce fading. First one is orthogonal frequency division multiplexing, also known as OFDM. In this process, the digital data is encoded on multiple carrier frequencies. The next thing is a MIMO, which is multiple input, multiple output. Multiple antennas at transmitter and receiver are used to enhance communication performance. The last one is rake receiver. It is a radio receiver that eliminates the effects of multipath fading. There are a large number of sub-receivers that decode a single multipath component, and the results from these dividers are all combined. From these receivers are all combined. Uh, this system is supposed to have a high SNR. Let us now take a look into my project. My project is based on a training based channel estimation of different channel and interference statistics for Rician fading. This is analyzed, and the structure that I have used is Kronecker structure with arbitrary sequence length, and have achieved the condition for optimal training length. And the next step is the training sequence that produces the minimum mean square error, that is MSE, is analyzed. From that, the minimum mean square error for channel matrix that is estimated for this minimum mean square error is analyzed, and the effect of spatial correlation on the optimal training length is analyzed. This project also analyzes the optimal training sequence on non-convex mean square error for squared Frobenius norm. Finally, the number of antennas on optimal training length of sequence is explained and evaluated. There are a lot of heuristics that are to be considered in the later sections of this project. First of all, mean square error and MMSE estimation. Mean square error is the trace of the covariance matrix CMMSE of the conditional probability density function that is averaged over Y. The equation for CMMSE is given below, and the equation for MSE, which is also known as MMSE, is given below. First of all, the most important thing to determine while determining MSE is that MSE is entirely dependent on the training matrix P. Therefore, Optimization of training matrix is very important to get a healthy MSE. There are a lot of heuristics that that are being proposed, and these heuristics are based on the total power. The total power is determined, and the shortest training sequence length for smallest MSE is also determined. Next comes the power allocation. The power allocation structure for Kronecker structure depends upon the covariance of the transmitter side matrix. Various heuristics are analyzed, and the shortest training sequence for smallest MSE is determined. Here is a theorem that describes the uh, way in which the power is allocated. The way in which the power is allocated. Uh, the first point that is to be noted is that disturbance should be weakest for the estimation of the strongest channel. This means that the strongest channel has the weakest disturbance. When the training power is high, the power is allocated to the m eigen directions that are statistically strong and root of m eigen directions of disturbances that are weak. When training power is low, the direction which has a minimum strong gain and weak disturbance is measured. The power is allocated along this direction. The main limitation of this theorem is that the power allocation is not considered. To reduce the above mentioned limitation, we all know that equal power allocation reduces mean square error. So if del t equal to 1 and sigma t equal to 1 and rr equal to sr, then power allocation is given as pj is equal to maximum of root of sigma j by alpha minus sigma j by lambda j at according to this equation. Next, we consider the optimal length of the training sequence. MSE with optimized training sequence is inversely proportional to the spatial correlation. This is the point where spatial correlation is introduced into our subject. If S equal to I, the training sequence used for ideal MSE is given in this equation. Optimal training sequence length is found out to be the rank of the training power, that is P. Therefore, for low MSE, the equation is given below. Next comes the squared channel norm for MMSE. In this, the Frobenius norm of channel estimation is considered. The training matrix is represented as P equal to UT dV power h to the base of Q. There are a set of solutions for which the Pj minimizes the mean square error. Each and every eigen direction carries a minimal amount of power. So this gives the MMSE for training sequence. MMSE for training sequence. In case of a Kronecker structured case, the equivalent MMSE and MSE are given by these following equations, which are derived from various heuristics. This is the power overall, this is the concatenated result for the optimal MSE and the power allocation phenomenon. Now let us take a look into our MATLAB codes so that we can discuss about the simulation. The first block that I designed in MATLAB was the Lagrange multiplier function. This calculates the power allocation, and the formula for this is given as follows. And then after calculating the power allocation, it calculates the deviation, which is given by this formula. The next function is to determine the MSE, that is function MSE matrix. MSE is defined as the trace of the CMMSE matrix, and then that is averaged over a length of y. So this formula realizes the MSE, and the third function written was to find the MSE normalized, which is the sum of all the eigenvalues and as a function of power allocation. The first simulation figure that I'm going to show, the first simulation figure compares the training power with the average normal MSE. Here the NT and NR are found to be 8 and 4 respectively. This shows that the MPU or ML optimal has poorest performance, and one-sided and two-sided optimal also has poorest performance. But the performance of MMSE heuristic and MMSE optimal are found to be nearly equal. Are found to be nearly equal. The next is the simulation for one-sided linear case, which is compared with all other estimators. In this, we have four estimators: MMSE, one-sided linear, MMSE, and MMSE optimal. This figure shows that the heuristic approach, which is defined as MMSE and whose results are based on the heuristic that is proposed, has a majority of gain, which is shown with this blue line here. The simulation number 3. This simulation is based on the variation of optimal length when spatial correlation is varied and analyzed. Here, heuristic and optimal are both concatenated into a single graph. The alpha values are 1, 0.66, and 0.33 respectively. So first, the nature of the simulation is that the correlation of random nature into the correlation is of random nature at the transmitter. So we can see that the spatial correlation increases with optimal training as the optimal training length decreases. Spatial correlation increases alpha equal to 1, alpha equal to 0.66, and alpha equal to 0.33. Spatial correlation increases as optimal training length decreases. So when spatial correlation increases, the optimal training length decreases. The next is figure 4, which is a normalized MSE for channel squared normal Frobenius form. Here also the MMSE is calculated in the indirect approach. It results in performance degradation, and this performance degradation happens at low SINR. Then the major conclusion that can be drawn from this approach is that in indirect approach, uh, performance degradation happens at low SINR. This is not asymptotically optimal at high SINR. The design of the training sequence plays a key role in the performance enhancement of the MMSE estimator. This is the main point that has to be considered. And when it can also be noted that, as mentioned in the previous slides, in our overview of the project, the number of antennas for optimal training length of the sequence is found out that for a long for a short number of for a chopped up that is mentioned in this report. In this report, we have mentioned that the number of antennas is larger than the optimal length. This is the wireless communication project that I have presented, and I would like to extend my acknowledgement to my wireless communication professor, Dr. Wu, at University of Florida, who has helped me a lot with the classes and helped me a lot with teaching the concepts of fading. And I would also like to reference my acknowledgement to the authors from whom I have got my various observations and who have helped me to move on with this project and complete it successfully. Thank you.